Hi. In the previous modules, we've talked about the multiple comparisons problem. We talked about two approaches towards making principal threshold of statistical maps, and these were the controlling for the family-wise error rate and the false discovery rate. In this module, we're going to compare the two methods a little bit. So here we see an example. Let's suppose that we have 10 images here, and in each image we have an area of activation in the center, denoted by white, and an area outside of this center, denoted in black, of no activation. We put noise on top of that, and we get a signal-to-noise image like we see at the bottom here. Now what we want to do is we want to threshold this image, assuming that there's no signal in any of these voxels. We want to threshold this image and see whether or not we can recover the signal or not, and see how many false positives we get, as well as how many false negatives. Here, in the first row, we correct using an alpha equal to 0.10, but no multiple comparison correction. In this case, you'll see that we get a fair amount of the true activations, so we're able to detect a lot of the true activations. However, we have an awful lot of false positives outside of the square. And so, in general, we'll see the percentage of false positives below each image, and they're on average around 10%. If we instead control for the family-wise error rate at 10%, we get a much more stringent threshold. In this case, out of all 10 images, only one of them gets one or more false positives, and that's going to be the 7th image here. You see that there's one false positive there. However, the cost we paid in having such a stringent threshold is, if you look inside the box, we're getting relatively few true positives, and so we're getting a lot of false negatives in that case. Now, if we look at false discovery rate correction at the 10% level, you see that we get something in between. Within the square, we were picking up most of the truly positive voxels, and outside we're getting a fair amount of false positives, but significantly less when we did no correction. Below each image, we see the percentage of active voxels that are false positives. So as it should be, in average, they're about 10% of all active voxels that were declared active or false positives. So we have significantly fewer false positives than we would have with no correction at all, but of course a whole lot more than if we did family-wise error rate correction. So family-wise error rate gives us the most stringent thing. So if we're really, really concerned about false positives, it gives us a strict control over that. But on the other hand, it gives us, much more false negatives in this case, while false discovery rate is somewhere in between that and no correction. In general, most published neuroimaging studies, such as PET and fMRI studies, use arbitrary uncorrected threshold. So they simply correct at some very stringent level, such as p less than 0.001, and don't use a multiple comparison correction technique. And the likely reason that people do this is that with the available sample sizes, corrected thresholds tend to be so stringent that power is extremely low. However, using uncorrected threshold is extremely problematic when interpreting conclusions from individual studies, as many of the active regions are bound to be false positives. And this will lead to false positives being introduced into the literature, and because the null findings are hard to disseminate, it's going to be difficult to refute false positives that have already been established in the literature, and this is not so good. Sometimes researchers use an arbitrary extent threshold when reporting results. So for example, a voxel is only deemed truly active if it belongs to a cluster of k contiguous active voxels. So for example, we might do a primary threshold of p less than 0.001, and then say, well, if 10 contiguous voxels are all below that threshold, then we'll deem that whole cluster as being active. Otherwise, the voxel is thrown out. However, unfortunately, this doesn't necessarily correct the problem, because imaging data tends to be spatially smooth, and therefore false positives may appear in clusters. In this example, we see activation maps with spatially correlated noise that's thresholded at 3 different significance levels. And so, due to the smoothness here, the false positive activations are going to look like contiguous regions of multiple voxels. So first, if we threshold at alpha equal to 0.10, we see that we get most of the truly active voxels, but we get a lot of false positives, and they look like coherent spatial regions. If we move to alpha equal to 0.01, we're getting less of these, but they're still getting contiguous regions outside of the truly active that look compelling. And the same is true if we do an alpha equal to 0.001. So the take-home point here is that because of the spatial smoothness in the image, we're bound to get false positives that appear to look compelling and look like kind of a blob of activation. And here's similar results using null data, and it tells the exact same story. Here there's no activations at all, but at varying threshold it still looks like we have compelling activation profiles. Okay, so that's the end of that module, and it's the end of our discussion about multiple comparisons. In the next modules, we'll start talking about connectivity analysis. Okay, I'll see you then. Bye.